All right, guys, I wanted to talk through atomic structure today. This will be section one of your notes for unit one. The problem of determining elements and their existence, what's in them, what are they made of, some key terms that we'll talk about. So this should be a pretty good little first lesson for us. How big or how small is an atom? Hopefully, you've had a chance to watch that already. I would suggest stopping here if you haven't. Go take a look at that. That's an excellent bunch of metaphors that kind of talk about how exactly small is an atom because they are ridiculously small. And it really kind of drives home the fact that these are, you know, almost invisible particles. But they play a huge role. There's some interesting properties about them as well. So again, I would check that out. That will be on the weekly agenda for the notes. So we'll take a second and stop here and check that out if you haven't already. A couple more, if you have watched the video, a couple more metaphors. Thinking about things that you might see the period, and that says the size of the period of your textbook would be the nucleus. The atom would be 5 meters in diameter, so somewhere on the realm of like 18-ish feet, give or take. The nucleus is the size of a basketball, and the size of the atom would be 4 kilometers, or almost 2 miles in diameter. So that's just kind of another reference to how small the nucleus even is, even inside an atom, which is already ridiculously small. We're going to talk about subatomic particles next. You've probably heard a little bit about these from your seventh grade, I believe it was, science class: protons, neutrons, and electrons. These are the major drivers of identity and then interactions that go on between atoms. Everything in gray you will want to take down. These are going to be your physical notes that you will turn in at the end of the week. You'll have two parts. This is part one. So protons are your first subatomic particles. They have a positive charge, P and P there, proton positive. You find these in the nucleus. They are about 1 atomic mass unit. An atomic mass unit is a almost arbitrary scale of measurement when you're talking about these things. But it does give you some size, some relevance, especially when we talk about the electron. And what's special about the proton is it gives its element its atomic number. This is the identity piece. You cannot have two elements with the same number of protons that are different things. So, for example, here you have nitrogen. You cannot have a nitrogen with 6 protons. That would be a totally different element. So this is what drives the identity of your element. Neutrons, neutral, neutrons no charge. These guys are found in the nucleus. They are also 1 atomic mass unit, so about the same size. But these contribute to the element's atomic mass. These actually do have a couple different purposes, a little bit further in than we need to talk about, but one of the main ones being keeping the nucleus balanced, keeping everything stable. They actually organize themselves with one another in the nucleus so they can just kind of minimize interactions between those protons and electrons. So they play a very important role, and that having the no charge helps them keep the balance, keep the peace, if you might, in the atom itself. Electrons, these are probably the most important, second to the identity piece. These guys are going to be the ones that are going to do all of the reacting. They're going to control properties. They're going to control, what happens between a sodium and a chlorine atom when they interact. These guys are going to be the major players moving forward. So much so that we'll have entire units based off of just the electron and what happens between electrons. They have a negative charge. They are found in what's known as a cloud or a shell outside the nucleus. So there's a lot of, again, empty space, which you saw hopefully in the video, where you have, just magnetic fields or almost nothing. That was the kind of the part of the video where he was falling through space, and he basically was hitting nothing except little magnets that kind of show that those do exist. And then the big piece of the size, we talked about the AMU and how that plays a role. The electron is 1/1840th the size of an atom's protons and neutrons. So they play a almost unimportant role, a insignificant role as far as the mass of an atom is concerned. As far as the size, they will play a little bit of a role when we talk about periodic trends. They'll kind of contribute to the size, but to the overall mass, they're essentially irrelevant. No atom to date that we know about has 1,840 electrons, anyways, to even equal one proton, and that's so that it would never even equal any of the smallest elements that would exist. If you want to actually see atoms, they probably something you will never get a chance to do. You may get a chance to do, depending on technology, as you go forward into your college careers. But NOVA does a really cool little exemplification of visualizing atoms, visualizing the motion of atoms, particles in some gases in this video. I will also link this in the agenda as well. If you want to take a look at that, it's pretty neat to say that you can, these are essentially invisible, but given the right medium, you can somewhat see these. Next, we'll talk about quarks. So quarks is a little bit beyond the scope of high school chemistry, but they do play an important role. It's essentially the fundamental particle in physics. So there are different versions of quarks. There's up quarks, down quarks, strange quarks. There are quite a few, and these are what are actually going to form what are called hadrons, which are the building blocks of protons and neutrons. So these are what are making up the subatomic particles. That's why I called them subatomic particles. And then there's a whole field of study based off just these guys alone called particle physics. Again, that's a little bit further than we need to talk about, but I think it's neat to at least mention that, because it's cool to think that these things are so ridiculously small, but things also make these things up, all the way down to, based on your theoretical beliefs of either string theory or whatever it might be. So there's this is only the surface level of chemistry, which we're going to talk about. Here's a little visual I like to show, showing the positive protons. So you got the little yellow happy positive protons, you got the neutral neutrons in there, and then you got the negative or upset looking electrons on the outside flying around. It just kind of visualizes the happiness, sadness, and the neutrality of the of the atom, keeping everything balanced. Charges, they are important. They are controlled by quarks and their magnitudes. The number-wise electric charge is insignificant for us, but I do want you to recognize at this point that they all have a specific charge. Protons are +1, neutrons are 0 because they're neutral, and then electrons are -1. And all that really has to do with is the exact opposite of the charges measured in coulombs of your subatomic particles. And then that neutron has no Coulombic charge, so that's why there's no atomic charge as well. How do elements differ? So what they're going to differ by predominantly at this point is going to be their protons. Those are going to be what identify your elements. So the different number of protons tell you which element you're talking about. That's going to be the case throughout all chemistry. Those are the identifiers. You'll notice in the list down here, there are the first 6 elements, noticing that the atomic number changes along with the protons. Neutrons will be a little bit different. We'll talk about that in the next set of video or the next set of notes, which contributes to mass, because we already talked about the neutrons contribute to mass. And then you'll also notice the electrons stay constant with atomic number. For right now, that's going to be the case. But once we get into ions, which are elements that change their charge, that's going to kind of differ as well. But for right now, we are good to assume neutrality, which is protons and neutrons, or protons and electrons being the same. So some quick definitions that you might want to have. Atomic number is the number of protons. We talked about that a little bit. If you already have that up there from somewhere, just highlight that, circle that. That is huge. That's going to be your indicator. Mass number is going to be your protons and your neutrons combined in the atom. So they make up the entire mass. So that's going to be called our mass number. You can actually do a little math and work out the different numbers of those things, which we'll talk about in the next one as well. It's predominantly your mass number minus your atomic number gives you your number of neutrons. So if you know your atomic number and you know your mass, you can obviously mathematically calculate what your missing piece is. So a little bit of keeping it straight, and then we'll call it for the day here. Atomic number is going to be your number of protons. It determines the kind of atom. It's the identity. The mass number is your protons plus your neutrons, and that determines an element's mass. We'll talk about electrons super specifically in the next couple of units. But I wanted to go ahead and give you a quick, brief overview of the atomic structure. Your POGIL will probably be your next course of action to introduce yourself to the next topic, hopefully, and then we will get started on the next section of notes. Do remember that these notes, along with part 2, will be due at the end of the week, and these are handwritten notes, just because rote memorization is so important in this subject. A lot of these words, a lot of these terms you've never heard before, especially once we get further in. So I do want to make sure you are taking notes and keeping up. If you have any questions, feel free to email me, ask me. Otherwise, have a great day.